So first of all, hi Murphy. Hello Wayla. Okay, so we are going to do a little bit about horizontal and oblique asymptotes. We'll address vertical again, but these are the two that are the main focus on this. All right, so every rational function that I'm going to present here is going to have the same domain. The denominator is x squared plus 6x plus 5, and we are going to initially set it equal to 0, but because it's a domain, we don't want to actually obtain those values. We want to stay away from those values. So we factor this into x plus 5, x plus 1. And we set each factor equal to 0, or really not equal to 0. And then we say, when we deal with this, we end up with x equals negative 5. And when we deal with this, we get x equals negative 1. But again, we want to avoid those values because those are the things that generate zeros in the denominator. So we say not equals, not equals. Now, there's nothing in the numerator that's canceling these factors out. So since nothing is canceling, and that's the indication for a point of removable discontinuity, these are vertical asymptotes, and I abbreviate them v dot a. So same denominator, sorry, same domain, same domain, same domain. Now, to be able to determine if you've got a horizontal or an oblique asymptote, the process is the same. It's actually a long division process. You'll see a quick approach in a second, but you basically take your denominator and you divide it into your numerator. And if we were to do that division, you'll find that since this degree is larger, it's 0 times. And so your horizontal asymptote, HA, is y equals 0, okay? So again, if the degree here is smaller than the degree here, horizontal asymptote is the line y equals 0, or the x-axis. Now, what if your degrees match? Well, let's see what happens, and please catch that this is 1 over 1. So we're going to do long division. Of course, we fill in with our 0. What do we multiply x squared by to get it the same as x squared? Well, we multiply it by 1. So we multiply this through by 1. We get that expression as the positive. So it'd be x squared plus 6x plus 5. But remember, we have to Frankenstein. So we draw the line and we change the signs. We're left with negative 6x minus 3. Now, this, and this is a little bit, I'm jumping ahead. What ends up happening is the remainder gets dominated by this x squared, and so you actually just end up saying, y equals 1, that's my horizontal asymptote, okay? Now there's the remainder term, and we'll talk about that in a second, but I want to point this out. You get the 1, you get 1 over 1. So if the degrees are the same, you can just quickly look at it and go, oh, the ratio of 3 to 1 is where our horizontal asymptote will be at. So y is equal to 3 over 1, which is equal to 3, okay? Now, what happens if this degree is 1 larger than this one? Well, you're going to get a division that has an x to the first, oops, I wrote that on the wrong spot, x to the first power, typo. I was looking through the camera and writing and it flips things around. Anyhow, so we take x squared plus 6x plus 5, and we're going to divide that into x cubed plus 0x squared plus 0x plus 1. We multiply x squared by to make it exactly the same as x cubed. Well, we multiply it by x. X times x squared is x cubed. There's my 6x squared, and there's my 5x. Frankenstein. Draw your line, change your signs, okay? So we're left with negative 6x squared minus 5x plus 1. What do you multiply x squared by to get it exactly the same as negative 6x squared? Negative 6. So negative 6 times x squared is a negative 6x squared. Negative 6 times a positive 6 is a negative 36x. And a negative 6 times a positive 5 is a negative 30. Draw your line, change your signs. That's why these are positive. And you're left with 31x plus 31. Okay, so you've got the line y is equal to x minus 6, x to the first minus 6, because this degree is 1 larger than this one. And you get this remainder term, this 31x plus 31 over the x squared plus 6x plus 5. And what I'm going to tell you is that as x gets super big, positive infinity or negative infinity, and you square it, it even becomes larger. Its magnitude is massive in relationship to this numerator. And so what ends up happening is your term here becomes huge, and so the ratio approaches 0. It's another way to think about it, and I'll just write this down real quick. So you have 31x plus 31 over the x squared plus 6x plus 5. I'm allowed to multiply a ratio or a fraction by 1. So I'm going to multiply by 1 over x squared and 1 over x squared. And if I pass that through, if I distribute it through the top, what I'm going to have, now give me a second, I'm going to write this carefully. It's 31 over x plus 31 over x squared. And what happens is your x's cancel. Well, that's the numerator. The denominator becomes 1 plus 6 over x plus 5 over x squared. Now, take a huge number and put it here. That becomes 0. 6 over a massive number is getting very close to 0. 5 over a massive number is getting very close to 0. 31 over x squared, very close to 0, very close to 0. So we end up actually generating 0 over 1 off into infinity. And so all we really focus on is this part, the y is equal to x minus 6. Now, we graph that. This is the actual line y is equal to x minus 6. We actually graph it as a dotted line. And it's not actually part of the graph. It's just what the graph approaches. And depending, I haven't done any of the graphing on the calculator, but depending, it does something, where it approaches the line, okay? Now, last comment. If this is x to the 4th and this is x cubed, this is x to the 5th, x to the 4th, x squared, x to the 5th, x squared, x to the 6th, x squared. You still do the long division process just like you did, but you end up getting and being able to determine what the end behavior is out on infinity. So let me turn the page real quick. So if you have an x to the 5th and then plus 6x, and down here you've got x squared plus 6x plus 5. Because this degree is 3 less than this degree, your oblique asymptote, it's not oblique asymptote, it's end behavior, is going to be x cubed plus something. And so your end behavior is going to act like a cubic. It's not going to act like it around the origin. Around the origin, it's going to do its own little dance. But around positive infinity and negative infinity, it's going to act like x cubed. Okay, hopefully that's helpful.